A tunnel through space. A shortcut through the billions of light years separating the farthest ends of the universe. It begs the question of how anything could bore a hole through space.
A wormhole is basically like a tunnel through space itself that can connect one region to another region potentially very far away. So to illustrate that, we're taking space and imagining it as this two-dimensional sheet of paper. So we have a wormhole mouth that you can go in, and then the other end is a place you can go out. So you imagine a tunnel that goes into there and comes out of there. And you might say, well, it would take me longer to get from one place to another if I went through that tunnel than if I just took the direct route through ordinary space. But the point is that Einstein tells us that space and time are curved, they're flexible. So we can imagine picking up this piece of paper and curling these two regions so that they're close to each other. Then you go into that end of the wormhole, you come outside the other end, and there's a shortcut in between them in which the distance is not that much. So the wormhole provides a way that you can travel what appears to be a very long distance in a very short period of time.
And it's for that reason that wormholes have found a special place in science fiction.
If you want to write a science fiction novel, you might want to be able to get across the galaxy very quickly, and you don't want to be limited by the speed of light. So a wormhole can be a shortcut. It can be a way to get around all of the space that you have to travel through. If you believe that the speed of light really is a speed limit, you can't go faster than the speed of light, a wormhole provides you a way, maybe, to still go slower than the speed of light, but get to where you want to go much faster because the distance is much shorter. It's really just a shortcut through space itself.
A wormhole might also empty into another time. That's because wormholes are portals through the fabric of space and time. While they could theoretically link different locations in space, they could also theoretically link up different locations in time.
Because space and time are mixed up together, you could actually not only end up in a different part of space by going through the wormhole, but you could also end up in the past. You could end up in a different part of time. You could go into your own past, then come visit yourself before you entered the beginning of the wormhole.
So you could have a wormhole that goes from your living room to your dining room. They might be 5 years apart. So you enter one this year, and you come back 5 years ago. And if you take the paper with you, you've got some good chances of doing well in the stock exchange.
Brands ngan tai ko ayan ste.
Brand Jama Lapa Nupyu Tabara.
Is time travel possible? Everyone has thought about time travel at least once in their life. Maybe you've wanted to go back in time and try to change something from your past. There's even a lot of science fiction movies out there that involve time travel, or were inspired by time travel in some way or another. But is it really possible to travel back or forward in time? And if it is really possible, what would we have to do in order to make time travel a reality? The very thought about time travel and what it would take to make it a reality is mind-boggling. It is something that scientists, especially astrophysicists, have long thought about. The most fantastic thing? It's probably possible. We should probably start off with the bad news about time travel. We probably can't travel back in time and watch the Egyptians build the pyramids. However, there are a number of theories that have suggested that it is possible to take a leap forward in time, but going back in time is far more complicated. That's not saying it's impossible, though. The great 20th century scientist Albert Einstein developed a theory called special relativity. While most people think of time as a constant, Einstein showed that time is an illusion. It is relative in that it can vary for different observers depending on your speed through space. The ideas of special relativity are very hard to imagine because they aren't about what we experience in everyday life. But other scientists have confirmed this theory. The theory says that space and time are really aspects of the same thing, which is called space-time. There is a speed limit of 300,000 kilometers per second, or 186,000 miles per second, for anything that travels through space-time. And light always travels this speed limit through empty space. So more about this illusion of time. Special relativity says that a surprising thing happens to you when you move through space-time, especially when your speed relative to other objects is close to the speed of light. Time goes slower for you than for the people you left behind. You won't notice this effect until you return to those stationary people. So as an experiment, let's say you were 15 years old and you left Earth in a spacecraft traveling at about close to the speed of light, and you celebrated only 5 birthdays during your space voyage. When you got home at the age of 20, you would find that all your classmates, who were the same age as you when you left, were 65 years old, retired, and hanging out with their grandchildren. The reason for this is because as time passed more slowly for you, you would have experienced only 5 years of life, while your classmates will have experienced a full 50 years. But there is something else under Einstein's theory of general relativity, and that is gravity can bend time. Picture a 4-dimensional fabric called space-time. When anything that has mass sits on that piece of fabric, it causes a dimple or a bending of space-time. The bending of space-time causes objects to move on a curved path, and that curvature of space is what we know as gravity. So how could we travel through space-time? One option would be a wormhole, also known as an Einstein-Rosen bridge. Along with physicist Nathan Rosen, Einstein suggested the existence of wormholes in 1935, and although we've yet to discover one, many scientists have contributed their own theories about how wormholes might work. Stephen Hawking and Kip Thorne are probably the most well-known. Thorne, a theoretical physicist at Caltech, even helped Christopher Nolan with the science behind Interstellar. So let's just assume that wormholes do exist. In the late 1980s, Thorne said that a wormhole could be made into a time machine. According to Einstein's theory of general relativity, a wormhole could act like a bridge through space-time by connecting 2 distant points with a shortcut. Certain types of wormholes, it's theorized, could allow for time travel in either direction if we could accelerate one mouth of the wormhole to near light speed and then reverse it back to its original position. Meanwhile, the other mouth would remain stationary. The result would be that the moving mouth would age less slowly than the stationary mouth thanks to the effect of time dilation. But wormholes are tricky. They create all kinds of paradoxes. For instance, through a wormhole, a person could see themselves as they were 1 minute ago. But what if that person used the wormhole to shoot his earlier self? They are now dead. So who fired the shot? It's a paradox. It just doesn't make sense. You might have seen some of this paradox stuff in a famous science fiction movie that had an interesting time machine. Bonus points for the viewer who can name the film. And back on the subject of time dilation, the clocks on the International Space Station tick just a little bit more slowly than clocks on Earth do. Since the space station is moving so fast and is affected by less gravity, time moves more quickly. It's also why no clock on Earth is perfectly accurate, since the effect of time dilation means that time moves more slowly closer to the planet's surface. You could say that everyone aboard the International Space Station is a time traveler. You can get a better understanding of how time dilation works by looking at GPS satellites. The GPS chip in your smartphone works because there are 24 satellites circling the globe at all times that triangulate your location based on how long it takes time-stamped information to travel to and from the device. However, scientists learned when building the system that the atomic clocks on GPS satellites do indeed run a little bit fast, since they are moving at 9,000 miles per hour in orbit. To be specific, they lose 8 microseconds a day. That's hardly perceivable, but it's enough to throw off the location data. And so, GPS technology makes adjustments to the clocks on board to account for the relativistic effects. The problem doesn't lie with the clocks. They run fast because time itself runs faster in space than it does down below. And the reason for this extraordinary effect is the mass of the Earth. Einstein realized that matter drags on time and slows it down like the slow part of a river. The heavier the object, the more it drags on time. And this startling reality is what opens the door to the possibility of time travel to the future. Right in the center of the Milky Way, 26,000 light-years from us, lies the heaviest object in the galaxy. It is a supermassive black hole containing the mass of 4 million suns crushed down into a single point by its own gravity. The closer you get to the black hole, the stronger the gravity. Get really close, and not even light can escape. A black hole like this one has a dramatic effect on time, slowing it down far more than anything else in the galaxy. That makes it a natural time machine. So, a supermassive black hole is a time machine. But of course, it's not exactly practical. It has advantages over wormholes in that it doesn't provoke paradoxes. Plus, it won't destroy itself in a flash of feedback. But it's pretty dangerous. It's a long way away, and it doesn't even take us very far into the future. Fortunately, there is another way to travel in time, and this represents our last and best hope of building a real time machine. You just have to travel very, very fast. Much faster even than the speed required to avoid being sucked into a black hole. This is due to another strange fact about the universe. There's a cosmic speed limit, 186,000 miles per second, also known as the speed of light. Nothing can exceed that speed. It's one of the best established principles in science. Believe it or not, traveling at near the speed of light transports you to the future. To explain why, let's dream up a science fiction transportation system. Imagine a track that goes right around the Earth, a track for a super-fast train. We're going to use this imaginary train to get as close as possible to the speed of light and see how it becomes a time machine. On board are passengers with a one-way ticket to the future. The train begins to accelerate faster and faster. Soon, it's circling the Earth over and over again. To approach the speed of light means circling the Earth pretty fast, 7 times a second. But no matter how much power the train has, it can never quite reach the speed of light, since the laws of physics forbid it. Instead, let's say it gets close, just shy of that ultimate speed. Now, something extraordinary happens. Time starts flowing slowly on board relative to the rest of the world, just like near the black hole, only more so. Everything on the train is in slow motion. It really is that simple. If we want to travel into the future, we just need to go fast, really fast. The fastest manned vehicle in history was the Apollo 10. It reached 25,000 miles per hour. But to travel in time, we'll have to go more than 2,000 times faster. And to do that, we'd need a much bigger ship, a truly enormous machine. The ship would have to be big enough to carry a huge amount of fuel, enough to accelerate it to nearly the speed of light. With a ship the size we would need, getting to just beneath the cosmic speed limit would require 6 whole years at full power. While time travel does not appear possible at this point in time, or at least possible in the sense that the humans would survive it with the physics that we use today, the field is constantly changing. Advances in quantum theories could perhaps provide some understanding of how to overcome time travel paradoxes. One possibility, although it would not necessarily lead to time travel, is solving the mystery of how certain particles can communicate instantaneously with each other faster than the speed of light. In the meantime, however, interested time travelers can at least experience it vicariously through movies, television, and books.
T-minus 40 seconds. Everything looks good for launch.
Have you ever fantasized about going somewhere special? Somewhere far from crowds? Off the beaten track? Somewhere out of this world? Is it time to catch a rocket to the red planet?
Mars is filled with mysteries. Volcanoes 75,000 feet tall. Huge canyons, 3,000 miles across and 6 miles deep. All kinds of interesting features.
Awaiting you is some of the greatest scenery in our solar system. On a world where water once ruled, then vanished into thin air, where lost microbe empires may still survive underground. We've seen the postcards, and we do wish we were there.
Just the thought of being in this
new world, a scene and landscape that no other person had seen before. I think there are a lot of astronauts that would sign up to that.
Go with throttle.
But don't be fooled. Nothing about going to Mars will be easy. Danger awaits you on this desolate beauty, and perhaps Martians too.
If we find on Mars evidence of a second independent origin of life, that's hugely profound because it tells us right away that life is common in the universe.
Mars, invaded by a robot, and perhaps soon by an Earthling like you.
Would I like to go to Mars? Oh, in a heartbeat. Absolutely. If there was any way for me to be going to Mars, I wouldn't be screwing around with robots. You know, I'd want to go myself.
There has never been a better time to boldly go where no human has gone before. To follow in the footsteps of our robot pioneers and visit the planets of the solar system. It's been said that the first person on Mars is alive somewhere on Earth today. Imagine it's you. What do you need to know? How might you get there, and what should you pack? What are some of the must-see sites, and what should you avoid? Think of this as your personal travel guide to exploring the Red Planet. Mars has always had a mystique. It's one of the easier planets to spot in the night sky. A constant dot of red light moving through the heavens. And now we know for sure that of all the planets, this red, rocky one is the most similar to home. Here are polar caps and sun-baked deserts, giant volcanoes and mighty canyons. Mars even spins at about the same speed as Earth, making a Martian day only about 40 minutes longer than ours. Although it's further out from the sun and takes twice as long to circle it, the long Martian year has identifiable seasons. And what's more, our two planets share a common childhood.
In many ways, it's a sister of the Earth. It was formed at roughly the same time, about 4.5 billion years ago, with a little change here and there. It also was formed of the same sorts of materials, bombarded by comets and asteroids. So it has the same delivery system we have.
Could life have been forged in the same way on both planets? When we sent the first probes to investigate in the 1960s, almost anything was possible.
Originally, in the popular imagination, we thought that Mars might be inhabited by whole civilizations, building canals and so on. And then the Mariner flyby missions really painted a very grim black and white view of Mars as being barren.
The pictures and data recorded by Mariner 4 revealed Mars to be a cold, barren planet.
We should be coming up on terminal sending mission 5638. SCS is close to vertical.
Still, NASA was eager to look for signs of life. In 1976, the Viking spacecraft arrives from Earth for our first close encounter. And there are still hopes of a welcoming committee. But both Viking spacecraft send back photos of nothing but rocks and sand.
We had cameras, so obviously if there was a yucca plant or I was hoping there'd be a freeway in the distance, but what the main thrust of Viking was actually was some chemical laboratories, and they looked for the chemical signs of life.
Even the dirt seems devoid of life.
There was always a chance that when they were so busy looking for microbes, there could be a large organism looking over their shoulder that they completely missed. But now we have enormous amount of imagery that shows nothing like a large organism. There are no cats running around, there are no bisons, there are no palm trees.
It seems Mars is not the kind of planet that gives up its secrets easily. But if you dig a little deeper, you soon find that this is a world worthy of a closer look. There are some basic things you should know about Mars before leaving home. Most days will be clear and sunny and cold. The average temperature on Mars is as bitter as midwinter in Antarctica. At about half the diameter of the Earth, Mars is a handy size, but it's much less dense than Earth, with about a third of the gravity. Surprisingly, the actual surface area is almost exactly the same as all the dry land on Earth, shrunk together without the oceans. Build a few freeways and you could drive around Mars in a couple of weeks. And driving around Mars is exactly what planetary scientist Steve Squires has been doing since 2004. Not in person, but via NASA's two off-road robot rovers, Spirit and Opportunity.
This time we are 5 minutes, 55 seconds after entry. It looks like nothing I've ever seen before in my life.
For all of us here on Earth, the snapshots sent back by these forward scouts are the next best thing to standing on Mars in a spacesuit.
We very consciously gave these robots some human-like qualities. The cameras are about this high off the ground. They're the same height as human eyes. It's the visual experience that you get from looking at the rover's pictures is intentionally like what you would get if you were looking at the visor of your helmet and a spacesuit on Mars. I really think that if you put somebody on my team who's been part of this mission for so long down at Eagle Crater or on the summit of Husband Hill, you'd look around and you'd say, yeah, that's about right. That's what I expected.
In the 4 decades since our robots first arrived, the once fuzzy ball at the end of our telescopes has steadily focused into a red planet we can understand. And it's not a welcoming place. The problem is the atmosphere is so thin and cold that water exists only as solid ice in the ground or vapor in the air, not as a liquid on the surface. You might see some fine wispy clouds high in the sky, but don't bother bringing an umbrella. The whole planet is drier than the dustiest desert on Earth. And there hasn't been a drop of rain here for millions, perhaps billions of years.
The thing that fascinated me was that we could see valleys snaking across the surface that had clearly been carved by flowing water. So this is telling us that in the past it was different, and not only that, it was different in a way that would have made it more suitable for life than it is today, and that I found truly compelling.
We are very convinced that at one time it was a very hospitable planet with liquid water and enough atmosphere to sustain a climate. And so now we're trying to understand how did it change, why did it change, and what still might be on Mars.
These are deep Martian mysteries. If Mars and Earth started as sister planets, did life once festoon the Martian surface? Might it still be there? And where did all the atmosphere and water go? Solving these puzzles has challenged our planetary explorers from the moment the first Martian postcards were sent back to Earth.
It's the fact that it is so much like Earth that kind of makes Mars such a special place.
Steve Squire's Martian Odyssey has taken him from pole to pole, visiting those places on Earth that share at least some of the same characteristics. They are extremely dry, extremely cold, or extremely dead. Death Valley is one of his favorites.
This is actually a really important place. It's a place we call Mars Hill. We first found this place about 20 years ago. In those days, the only successful landings that had taken place on Mars were the 2 Viking landers. And they landed in places that looked very much like this.
In order to plan for the current Mars mission and to test the cameras and other equipment, NASA needed a good Mars look-alike. They found it at Mars Hill.
To your eyes, the main way in which Mars would look different from this scene would be the color. The color of the sky, and the color of the rocks, and the color of the soil. The colors on Mars are painted from a very narrow palette.
The color palette here is based on rust, rich in iron oxides. The rocks and soil and the rusty dust are always blowing around in the freeze-dried atmosphere. You won't see any blue skies in the tourist brochures for Mars. Instead, they're amber. Not only do the dust particles add a rosy blush to the sky, they also scatter sunlight in a way that turns the color of the Martian sky upside down to human eyes. Red by day, and blue at dawn and dusk. This is a sunset as seen by Spirit, a cold blue sun dropping over a distant alien horizon. Looking up into the clear, starry skies from the surface, you would see Mars's 2 tiny moons, Phobos and the smaller Deimos. With all the grace of a space potato and barely 17 miles long, Phobos has been targeted as a potential stepping stone for the first human mission to Mars. A test run before attempting the fuel-hungry and risky trip to the planet below. Dreaming about Mars and actually going there are 2 very different things. Mars may be our neighbor, but 35 million miles to the closest point is still a very long way from home.
To put humans on the surface of Mars, someone once joked there are only 3 issues: getting them there, keeping them alive while they're there, and getting them back.
That's a good step. Yeah.
Our space-age dreams of off-world colonies on the Moon and Mars faded with the cancellation of the Apollo program and the last trip to the lunar surface in 1972. It didn't stop us from traveling. We simply switched from astronauts to lower-cost, lower-risk robotic explorers. And when it comes to Mars, it's probably just as well.